Hello student, the question says a large solid sphere with uniformly distributed positive charge has a smooth narrow tunnel through its center. A small particle with negative charge initially at rest far from the sphere approaches it along the line of the tunnel, reaches its surface with speed v and passes through the tunnel. Its speed at the center of the sphere will be. So basically, this is the diagram situation. We have a large sphere with uniformly distributed charge. So there is a uniformly distributed charge, and we have a charge minus q rest and very, very far. Initially, they are very, very far. Now, this positive charge will attract this negative charge, isn't it? So because of attraction, my negative charge would slowly start to move. It will start to move towards this. By the time it reached the surface, it is accelerating because when it comes closer and closer and closer, the speed would keep on increasing. It's accelerating. So by the time it reached the surface, its velocity was v. Its velocity is given as v. Now once it reaches the surface, then what happened is that then it entered inside. Okay, it entered this tunnel. He has given the word very narrow tunnel. The reason why this tunnel is very, very narrow is that he indirectly want to tell that because of this tunnel, there is not much change in the formulas that we use for a sphere. That's why this word narrow tunnel is used. So it went through this and then it came to the center of this. Now, if the speed on the surface is v, he is asking what is the speed once it reaches the center of this. Before we solve this, we have to understand a little bit about a solid sphere. So let us look at the formulas of solid sphere. Suppose if you have a solid sphere, the potential formula are different inside and outside the sphere. So potential inside a solid sphere, not a shell, a solid sphere, it is not straightforward. It will be slightly complicated. Right now, I won't get into the derivation of this. So just remember k cube by 2r cube into 3r square minus x square. K is 1 by 4 pi epsilon naught. So 1 by 4 pi epsilon naught q by 2r cube into 3r square minus x square, where x is the distance from the center. So x is the distance from the center of this. So this will be the typical formula. At x equals to 0, if I substitute x equal to 0, you will get 3 by 2 kq by r. At x equal to r, so exactly at center. So once the particle reaches the center, what is the potential at the center is substitute x equals to 0 over there. You will get kq by 2r cube into 3r square. So indirectly you will get 3 by 2 kq by r. Next, what is the potential on the surface? Substitute x equal to r, you will get 3r square minus r square, 2r square. So potential on surface would be k q by, we'll have r. So this will be the potential on the surface because 2r square by 2r cube would be kq by r. So if it is positive charge, inside it is at high potential, outside it is at low potential. Because inside the potential is 1.5, outside it is at low potential. Indirectly, what does it mean? If you have a positive charge coming towards it, it will experience, it does not want to go inside. So anyway, these are the formulas for potential at the center on the surface. These are very critical in solving this problem. Then what about potential outside, some random point here? If you want potential at this random point, let us see what's the formula. So potential outside is just like any point charge, k q by x. You will assume all the charge is concentrated at the center. X is always, remember, x is measured from the center of the shell. So these are the typical formulas you should know before solving this problem. What is the formula at the center? What is the formula on the surface? What is the formula outside, inside? And mark these formulas also for examinations. Now let us look at our scenario. If I take this scenario, originally they are very far. So, and this is at rest. Let us find what is the initial energy of the system. The initial energy is potential energy plus kinetic energy. Potential energy is K Q into capital Q divided by the distance. Basically, I'm multiplying charge with potential. Potential is KQ by X. X is very far. Since they are very far, if you notice it, he has given originally the body is initially at rest and far from the sphere. If it is very far, it is infinity. The distance is infinity between them. Plus, initially it is at rest also. There is no kinetic energy. So, what is the initial energy of the system? It is directly zero. There is no initial energy. If there is no initial energy and there is no external force, it is getting attracted only due to internal force. Since there is no external force, we can assume safely that final energy is also zero. That means one energy only can be converted into another form of energy. Even though the body got kinetic energy, since the body gained some kinetic energy, its potential energy would counterbalance it. Even though the body has the kinetic energy, potential energy of the system would counterbalance it. So one form of energy is getting converted into another form of energy. So original initial energy is zero. Now let us look at various scenarios in this. This is very important while solving the problem. Now in this situation, I will make it a little bit small. Let us assume my charge has traveled and finally came here with speed v. Okay, so let me call this as some point P. What is the energy at point P? Energy at P is simply half m into v square because it got some velocity plus potential energy is it is still on the surface. On the surface, so potential due to q into charge minus q because potential energy is charge into potential. So half mv square minus q into kq by r because this is exactly on the surface of this point p is exactly on the surface of this. So kq by r, we know initial energy is final energy. So if this is energy at p, this is initial, I can just equate this to 0. So I'll indirectly get half mv square equals to kqq by r. This information is useful when I'm trying to analyze the third scenario. So in the third scenario, now this entire thing, same thing. Now my particle went inside completely. Now it is completely inside. Once it is completely inside, let us try to identify. Let me call this every time I'm selecting PQR. So let me call this EMN to avoid any confusion. So this would be M. And let me call this center. Okay, once it reaches the center, so energy at center. Let us assume it has a velocity v1. So half m into v1 square. This charge traveled here at v and it reached the center now. So let me call this v1 half m v1 square plus potential at the center into charge minus q. So half m into v1 square plus minus q into potential at the center. We have just seen 3 by 2 kq by r. So this is the potential at the center. So I can simply write half m v1 square minus 3 by 2 kqq by r, and this also must be equal to 0 because at any location the energy is conserved. So here also this must be equals to 0. So I can write half m v1 square equals to 3 by 2 kqq by r. But I want the answer in terms of this velocity. Since I want the answer in terms of this velocity, we know kqq by r is equivalent to half mv square. So in place of kqq by r, I will equate half m into v square. Now compare these two equations. We finally got half m into v1 square equals to 3 by 2 into half m into v square. If I cancel half m and half m, I will get v1 square equals to 1.5 v square. So v1 is basically root 1.5 into v. So root 1.5 into v is my option D. So the correct answer for this would be option D. What's the key concept in solving this problem? The key concept in solving this problem is you should first know what is the formula for potential inside a solid solid sphere with uniform charge density. You can think like an insulator with uniform charge density. So potential inside a solid sphere with uniform charge density, it will be kq by 2r cube. From this we'll find what is the potential at the center, so that eventually we can find potential energy and potential on the surface. Once we know these two, then another key point is that when they are very far and it is at rest, their initial energy is zero, which is very critical while solving for surface and this one. Once you understood these two, for surface we wrote and we identified the relation between this one and this one. We used this relation when we wrote the energy at the center and we have solved the problem. Hope you understood how I have solved. Thank you.